Hello everyone. Okay, so this time we're going to have a little look at some of the characteristic chemical behaviour of elements from the P block. So where is it? Here it is. The P block includes all the elements from group 13 through to group 18. Again, why we call this the P block will become clear later on in the course. Actually, sometimes it's quite useful to consider the elements in the S block and the P block together, taking out the inner and the outer transition metal elements and rejoining up the S and P blocks. We get what is known as the main group elements. These are exactly the 8 columns of Mendeleev's original periodic table. Just as group 1 and group 2 in the S block have specific collective names for all the members, so do some of the groups in the P block. The last column, group 18, are known as the noble gases. They used to be called the inert gases, but it turns out that they're not always so completely inert. Group 17 are collectively known as the halogens. You probably know that, but less well known is that the elements of group 16 are called the chalcogens, and their ions are called the chalcogenides. And not many people know that the group 15 elements also have a collective name. They are the pnictides. I'm sorry to say that group 14 and group 13 are simply known as group 14 and group 13. I do think we need to invent a name for these ones. Feel free to make any suggestions here. The order of the elements in the main group of the periodic table is very successful in organising their very many characteristic properties. Let's have a look at just one of those. So one obvious feature of many elements is that many of them are metals. Although sometimes even this simple question, is a particular element a metal, can be problematic. There are a number of elements that show intermediate behaviour. By some measure they look like a metal, but by some other measure they do not. We call these ambiguous cases metalloids. Looking at where the metals, metalloids and non-metals are in the periodic table is very revealing. Somehow the table, based upon an element's characteristic mass, and the stochiometry of some of its compounds, has grouped all of the metals together, and the metalloids are found at the interface between these two exclusive regions. More explanation of why this is will come later. Okay, here's another feature we could look at. We could compare how the atoms of each element usually arrange themselves in the pure element. Let's take a look at the first row of the P block. Boron actually exists as a number of distinct allotropic forms. While each of these is slightly different in the arrangement of the boron atoms, all of the allotropes of boron contain icosahedral clusters of 12 boron atoms. So typically each boron is surrounded by 5 other boron atoms. The next element is carbon. Here graphite is the lowest energy structure, diamond only being obtained under high pressures. In the graphite structure, each carbon atom is coordinated or bonded to 3 others, to give a network of 6 membered rings, often referred to as a honeycomb structure. In the element nitrogen, which is a gaseous material, each nitrogen atom sticks very strongly to just one other nitrogen atom. Thus nitrogen forms a diatomic molecular species, which you can call dinitrogen. While the bonding between a pair of atoms in nitrogen is very strong, the interaction between different molecules is very weak. A similar situation exists for oxygen and fluorine, and by the end of the line we get to neon. Atoms of this element refuse to stick or bond to anything, causing this element to exist as a monatomic gas. Okay, so let's have a look at the next row. Aluminium is a true metal, and it has a very dense structure. It is in fact a close packed structure, the sort of structure that is very common amongst metallic elements. Here, the aluminium atom is surrounded by 12 others. Next to aluminium is the metalloid silicon. Silicon has the same structure as diamond, each silicon atom being connected to 4 others. And next is phosphorus. It is well known that phosphorus exists in a number of different allotropic forms. But in white phosphorus, the molecules are made up of 4 phosphorus atoms on the corners of a tetrahedron. Here each phosphorus atom is connected to 3 neighbours, which is actually also the case in all its other allotropes. Until recently, it was thought that sulfur had the greatest number of allotropic forms. That honour has now been claimed by carbon. We normally think of sulfur as existing in S8 rings. In this way, each sulfur atom is bonded to just two others. Chlorine, well, that's like fluorine, a diatomic gas. And argon, that's like neon. It doesn't stick to anything much, especially not itself, and so that's a monatomic gas. The take home here is that metals need to have this dense, close-packed structure, and as we move across the main group, we see a transition to more open and more molecular structures. Okay, so what features are characteristic of the compounds of p-block elements? To start with, this is very challenging because there are simply so many compounds. Even thinking about simple binary compounds that just contain two elements from the 50 main group elements, that's 1,225 combinations. And with a particular combination, there may be one, some, or many distinct known compounds. Here's what I mean. If we take the combination of lithium and nitrogen, there are, at present, two known compounds. The first is a simple ionic salt, lithium nitride, where the lithium is a cation with a +1 charge, and the nitrogen is an anion with a -3 charge. This compound must have an Li3 N1 stochiometry in order to be charge balanced. But there's another compound with a composition Li1 N3. How is that possible? Well, it is an ionic material, but it's a little more complex. The lithium is, as usual, a cation with a 1+ charge, and that means that the N3 part must have a net charge of -1. Well, it does. The anion is a molecular anion. It is the azide ion, which is a linear arrangement of 3 nitrogen atoms, a triatomic monoanion. What if we'd hit upon the combination of just hydrogen and carbon? There is literally almost an infinite variety here. We can readily see that for each relatively simple stochiometry, there may be very many distinct stable arrangements of these atoms. In other words, very, very many distinct compounds. One difference between the lithium-nitrogen pairing and the carbon-hydrogen pairing is that the lithium-nitrogen contains compounds that must be ionic and must form extended lattices, while the carbon-hydrogen pairing results in many discrete neutral molecules. This is a key contributing factor to the complexities of these systems. Of course, the carbon-hydrogen thing is so complex it accounts for a whole branch of chemistry. So this is a key feature of the chemistry of the p-block and the main group elements, that in their elemental forms and in their many compounds we see a crossover from dense solids or ionic extended lattices to covalent molecular structures, and this range in the nature of bonding is also adding to the diversity of structures and characteristic behaviours. So let's take a step back and have a little look at the formation of ionic compounds or salts. To form a salt you need both a negatively charged species and another positively charged species in the same compound. We can look at the main group and we can see which elements form ions. Let's start with the anions, the negatively charged ones. Which elements form anions? How commonly do they do that? And what are their normal charges? The halogens in group 17 all commonly form a halide ion with a 1- charge. But this behaviour becomes a little bit less dominant as we descend the group. Compare that with the chalcogens. They form chalcogenide ions with a -2 charge. Then on to group 15. Actually only nitrogen occasionally and phosphorus rarely form a simple anion, and when they do, they form a 3- species. There are only a couple of examples of carbon forming a carbide C4- ion, but they do exist. You can clearly see the pattern here on this table. The other half of forming a salt is to look on the periodic table to see where it is that we form positively charged cations. The answer is on the opposite side to where we find the anions, and it clearly matches up with those elements that are normally metallic. So we've already met the ionic chemistry of the S block elements, but we also find that the metallic elements in the P block can also form cations. Looking at this data, we notice a couple of interesting trends. The cation charge increases by +1 each time we move to the right and into the next group. Also, it becomes less common, less likely that we will form these more highly charged cations. In addition, we notice that the lower part of this corner of the P block, the elements can sustain the formation of one of two possible charged states, and the observed pair of values always differ by 2 units. From this graph of cations and the graph of anions, we can make some simple predictions about which salts may exist, which compositions would be acceptable. In fact, regardless of the nature of bonding, ionic or otherwise, it's quite useful to look at the stochiometries of known compounds across the whole of the main group, and for simplicity, if we choose to look at all the known fluorides, this will tell us much about what is stable and what is not. So, if we take the very first row, with hydrogen and helium in it, hydrogen fluoride has a 1-to-1 stochiometry, and helium does not react with fluorine, so has a 1-to-0 stochiometry if you like. Now move to the second row. Lithium, beryllium, boron and carbon show a clear progression in which the proportion of fluorine in the compound is increasing. After that, nitrogen, oxygen and fluorine and neon show a steady decrease in the proportion of fluorine. The next row is from sodium to argon, and it shows a very similar pattern to the previous row, but it's changed a little bit. For phosphorus, we now see a new 1-to-5 stochiometry. In addition to the phosphorus trifluoride, you can now get a bottle of phosphorus pentafluoride. Notice that phosphorus tetrafluoride does not exist. There is no PF4 molecule. Sulfur and chlorine also show new stochiometries. We can get sulfur difluoride, sulfur tetrafluoride and sulfur hexafluoride. Each of these distinct compounds has its own reactivity and own chemistry. But again, notice that sulfur trifluoride or sulfur pentafluoride do not exist. It's a similar story for chlorine. In the next row, we've extended the range of the known compositions a little bit more. And in the row from rubidium to xenon, we've filled in a few more gaps. Notice that xenon now forms 3 distinct fluorides. Notice also that the many gaps where compounds don't exist are in a very clear pattern. Why we can't have tellurium trifluoride or iodine hexafluoride, we'll find out later on. Suffice it to say that in the P block, covalent bonding can be very important, and with covalency comes molecular species with particular shapes and geometries. I want to give you a sense of the types of molecular structure that we find in this part of the periodic table. Usually, the largest atom is at the centre, and the smaller atoms are peripheral, usually in a very specific geometry. How we can predict the geometry is something that we will look at in some detail a bit later on. Okay, so the last thing I want to talk about here in relation to the P block is the formation of oxyanions. We've seen which elements form simple monoatomic anions, but many more elements react with oxygen to form more complex polyatomic molecular anions. I'm just going to pick out a couple of related series of ions. So there's a whole series of important trigonal planar oxyanions that start with BO3 3-, the borate anion. Next to that is CO3 2-, the carbonate anion, and after that is NO3 1-, the nitrate ion. Notice that they all have the same sort of structure, and that with changing the central element, the value of the charge changes by just 1 unit for each change of group. Now if we go down a row and consider the oxyanions formed from the row below, things change. Now the stable species has 4 oxygen atoms around the central atom. These atoms form a tetrahedral structure. So for aluminium we can find, although it is quite rare, an AlO4 5- anion. This is the aluminate anion. Moving over to silicon, we can have in certain solids the silicate anion SiO4 4-. After silicon is phosphorus, and we have the very important PO4 3- phosphate ion. Then the sulfate ion, SO4 with a 2- charge, and after that the perchlorate ion, ClO4 1-. Notice the wide range of stability associated with this type of anionic structure. You might wonder about the next element, argon. Could you get ArO4 as a neutral compound? Well, the answer is no. The compound does not exist. However, if you drop down the group a couple of places to xenon, well, XeO4, xenon tetroxide, that is known. You can put that in a bottle if you like, but beware, it has a tendency to explode. So what I've shown you is some small number of important compounds. Clearly main group chemistry is a huge subject, and in these few minutes I've just tried to give you a flavour of some of the characteristic chemistry of this part of the periodic table. Okay, thanks for watching.